And welcome back. It is Friday, July 10th. Good to see you. It's almost the weekend, not quite. Don't celebrate yet, but we've got a couple things to go over. The last part of chapter 20 we'll be finishing off. So, homework 5 is due tonight associated with that chapter. And also, the second hour here of class will be starting chapter 21, aldehydes and ketones, more reactions there. In chapter 20, we've already seen a lot of reactions with aldehydes and ketones, mainly hydride and carbon nucleophiles, the Grignard reagents, the organolithiums, the cuprates. So there's a lot reaction-wise. So I'm warning you again, these next couple chapters are very reaction heavy. So focus on reactivity there, definitely. And then homework, you should be fine on that. Let's start by reviewing some things. So this is a little in-class quiz, you could say. If you want to pause, you can work these problems here. We got 7 problems, and we are back. Let's see what your answers are here. So we've got sodium borohydride with a ketone and then quenching with water. We often draw that as a separate operation in the same flask. Remember, you just dump in the water or dilute acid. And so what do we get here? The hydride nucleophile, you can imagine it like that. That's fine, but it's really the borate, the tetrahydridoborate. Hydride does come off. So thinking about the mechanism, we attack the electropositive carbon and then quench with water. So what do we get from a ketone? Right, we get a secondary alcohol, okay? If that was an aldehyde, we would have gotten, what, a primary alcohol. But that's what, a reduction. Remember we talked about reductions and oxidations in general. Lithium aluminum hydride has the acronym, the abbreviation there. It's the more potent reducing agent. It can reduce a lot of different derivatives, including esters here. And remember, there's 4 hydrides here. All 4 of them can transfer off each reagent. You only need a 4th of equivalent. So even though we're just drawing 1, remember 2 of the hydrides will participate here with this derivative of carboxylic acid, the ester. And what do we get here? Yeah, we get the primary alcohol, okay? Remember, phenyl is the abbreviation for benzene. So imagine 2 hydrates going in here. The leaving group, it's the ethoxy group. Tetrahedral intermediate, remember we examined those carefully. You can bring the electrons back down, kick off ethoxide. Actually, it's associated with the aluminum at that point. Then another hydride can add there to give the primary alcohol. Okay, how about this one? PCC, pyridinium chlorochromate, can do the partial oxidation of primary alcohols. That's where it's important. It can also oxidize secondary alcohols to ketones, but with primary alcohols, PCC will stop at what? Stop at the correct aldehyde stage. And that's very important for synthesis. A lot of times we start with alcohol starting materials. We need to make aldehydes or ketones that we can then add more nucleophiles to make more complex structures. So PCC is often one of these enabling steps in a multi-step synthesis. Then we've got the cyclopentanone. That's not a double bond there. Sorry, that's on the board there. And then we've got the propyl Grignard, propyl magnesium bromide, and then quench with water. Remember, these are carbanionic. The nucleophile is carbon here. So we put a 3-carbon unit onto this ketone, and then what? Quench with water. So we get the 3 carbons there, and we get the, tertiary alcohol from a ketone. Remember, we focused on the structure of the carbonyls. With formaldehyde and Grignards, you get a primary alcohol. Aldehydes and Grignards, you get a secondary alcohol. And with ketones and Grignards, you get the tertiary alcohol. Okay, but that's the bond we make right there. Okay, so keep track of what's going on there. How are you doing so far on the quiz? Okay, it's not a quiz, don't worry. It's just a quick review here. And then we've got ethyl cuprate here with an enone alkene ketone, and that adds at the beta position. Remember, we have the enolate intermediate. That enolate is resonance stabilized. Why do we have to go through the enolate? How come we just don't add at the carbonyl position? Why at the beta position? Well, because the cuprate's less reactive, it needs a more stable, resonance stabilized intermediate. So it adds at the beta position. And then you have the enolate, and then you quench with water. You protonate at the alpha position. Remember, we had these two designations, alpha and beta positions. Those are just mechanistic markers. It's not part of the naming. But what it's the product, you get the ketone back out. Ketone looks like it doesn't undergo the reactivity. But no, it's the polarization, that resonance stability of the ketone that makes it add here. Cuprates do not add to simple alkenes. It has to be an enone, okay? We get the product there. Okay, dibol with an ester, dibol diisobutyl aluminum hydride, quench with water. And what do we get here? We stop at the aldehyde stage. So it's kind of like PCC that does the partial oxidation. Dibol does the partial what? Reduction. Okay, and it is a hydride, but it just has the one hydride group. So it can just transfer once. The tetrahedral intermediate breaks down and gives you the aldehyde product. Okay, how about benzoyl chloride? This is from benzoic acid, phenols, benzene, and the acid chloride with excess methyl magnesium bromide. Yeah, this will go to the tertiary alcohol. So your tetrahedral intermediate has the chloride on it. Maybe we could review that quickly. So O minus chloride, and there's the first methyl that adds, and then in the reaction mixture, good leaving group on chloride can give you the ketone. Remember, there's a name for that, acetophenone, and then your second equivalent can add. So that's excess, and we'll usually specify that, hopefully. But acid chlorides and esters with Grignards go all the way. So we could do the same thing here with this this substrate with the Grignard. That would add twice there. Anyway, that's a lot from chapter 20 to review those things. What I'd like to do, the last part of this first hour, is to do some synthesis problems. The protecting group issue, the tert-butyl dimethylsilyl protecting group. I'll show you why that's important sometimes. And yeah, some other multi-step synthesis problems. So the first one I'd like to show is this one. How would you make this from a simpler compound that has 4 carbons or less? So how do we make this from something that has 4 C's or less? And the cheaper type of starting materials are alcohols. So how would we make it? So this has 6 carbons, okay? It has the alcohol at the 2 position. What are the strategic bonds? And that's what I'd like to get you to focus on. And in 351, we've done a lot of multiple step synthesis problems. And again, we talked about strategic bonds. What's that? What do we mean by that? Well, it's a bond that can be made by a reaction an enabling reaction. And the very powerful reactions we've seen in chapter 20 are the Grignard reactions that can make carbon-carbon bonds. So where are the bonds we could make? Well, right here. I view that as a strategic bond because you see then it liberates a 4-carbon intermediate and then a 2-carbon intermediate. What would that come from? So this open arrow here means retrosynthesis. Retro meaning backwards, and so here's what we want to make. So in the backwards direction, if we break that bond right there, what would it go back to? Yeah, an aldehyde right there, okay? 1, 2 carbon, so acetaldehyde. And then the 4-carbon unit would need to be a nucleophile. So how about the Grignard reagent? So here's N-butyl magnesium bromide. So if we react those two together in the forward direction, you see, and then quench with water, we could get that product. So yeah, so that we view as a strategic bond. Not here, okay, not here. Okay, there are ways to put those type of things on there. You could think of a cuprate adding here if we had an unsaturated group and then a ketone there, and then reducing a ketone. Maybe we'll show some alternative ways. Well, there's also this way right here. Maybe we could look at that one. That would come from this aldehyde and what? Methyl magnesium bromide. Okay. So there's a couple approaches there to get that. Okay, but that's a 1, 2, 3, 4, 5 carbon species. I'm saying, 4 carbons or less because those becomes a bigger fragment. How do we make this from an alcohol? Yeah, we'd have to make it from this ethanol, and then what we'd have to do? Yep, PCC, pyridinium chlorochromate. Stop at the aldehyde stage there for the oxidation. What about this? How do we make that? Well, that's from the bromide and magnesium. Okay, magnesium in THF. Sometimes we specify the solvent there. It can't be water or an alcohol. It has to be an inert polar aprotic solvent there. So magnesium would insert and make that. Okay, that maps back to an alcohol, 4 carbons or less. What about this one though? That's not an alcohol. How do we make that from the alcohol? So we'd have to make it from this. There's a couple ways to do that. Yeah, HBr. Now that's from 351. Now be careful with HBr though. If it's a branched alcohol that can rearrange to a more stable carbocation, it will. The more useful reagent here is actually phosphorus tribromide. Okay, that one converts alcohols into bromides without any rearrangements. So this is kind of the important one to use, and it's not acidic, it's not corrosive like HBr. So the phosphorus tribromide is really the more efficient way to go there. But that, allows us to make this alcohol starting from these simpler, cheaper alcohols in a few steps there. But you can see how the multi-step synthesis works there. All right, let's look at another one. And again, this combines with the 351 reaction a little bit. How would we make this alkene? Now, alkenes are made from elimination reactions, right? And a couple different elimination reactions, E1 reactions, E2 are probably more efficient there. We also know what? Alcohol dehydration reactions. And that turns out to be the way this thing is made. It comes from this tertiary alcohol, and then you just treat with sulfuric acid and heat, okay? And the heat drives off the water, remember that? So alcohols can be protonated. It's a tertiary alcohol, it's already stable. And then we form, according to Zaitsev's rule, right, the more substitute alkene. We'd not want to form this alkene from that dehydration, okay? This is the more substitute one. That one is the major product. So how do we get this from simpler materials? Well, we can make it from the ketone, right? Cyclohexanone, and react it with what? Methyl magnesium bromide, and quench with water. And yeah, that will get us there directly, 2 steps there. And combined with the dehydration reaction, we could form the tosylate, do an E2 elimination, or form another leaving group. E1 wouldn't be very efficient there. We get a lot of substitution. But this dehydration is very good for tertiary alcohol, giving the more substitute alkene. Anyway, that's a simple procedure. I'll show you later in chapter 21 how to make these less substitute alkenes directly from ketones using the Wittig reaction. That's coming up. All right, let's see if you can do this one then. A couple different ways to approach this one. Let's see, let's make it from alcohols, 4 carbons and less. So it's a little bit more complicated ketone, you could say. It's got some branching there. Where are the strategic bonds? Yeah, right here or here. Okay, let's look at this one right here. There's a couple ways we could do that, but let's go back retrosynthetically to an alcohol. Now, if we have an alcohol there, that opens up the possibility of the Grignard reaction, right? So we know the forward reaction here, PCC. Yeah, it oxidizes secondary alcohols. Ketones. We could use chromic acid there. Similar result. That's the fully oxidized thing from a secondary alcohol. But when we're here, look, this bond then becomes strategic from what? From a Grignard point of view. We've got this aldehyde, and then plus we've got this Grignard reagent. Okay. And let's see. What do we we get there. We get the Grignard reagent. The aldehyde would come from what? We'd have to come from the alcohol, again PCC, and the Grignard here would have to come from the bromide. Yep. And notice, we've got branching here, so you definitely want to use what we say, phosphorus tribromide would definitely be the way to go there. If you use HBr on this alcohol, it'd do the shift here, and you get the tertiary bromide, not the one you want in the primary. So phosphorus tribromide is really a good way to go there. Let's see. We've got this alcohol up here. Now that's already 4 carbons or less. I'd like to show you how to make this alcohol using a methyl Grignard reagent, and this one, so the methyl magnesium Grignard, and let's use ethylene oxide. So here's a 1 carbon Grignard, right, from bromo methane, and then put in ethylene oxide, and look, after quenching with water, you get that, okay? And then, yeah, PCC to the aldehyde, and then you can combine the two. Remember the ethylene oxide, the epoxide thing is a great way to extend Grignard reagents by 2 carbons, okay? And it always adds at the less substituted spot, so that can be a very useful reaction there. All right, there are limitations to the Grignard reagent, and what did we say there, solvent-wise? The Grignard reactions and forming the Grignard reagents, you have to have aprotic solvents, right? Inert solvents. Nothing with a pKa that's low enough that can be easily deprotonated by the Grignard reagent. Let's point out an example of that. Say we've got this ketone, and we want to add methyl magnesium bromide to it, okay? And our desired product, you see after quenching here, is this. Okay. That's what we're trying to make. From the ketone, we're trying to make this tertiary alcohol. There's a problem here, right? We've got an alcohol here which has a acidic enough proton. Remember, the pKa of alcohols is about 16 to 18 or so. And these are very basic here, right? So this can just take that proton off. And what we get here is the alkoxide. And what's the byproduct here? Methane, which just bubbles out of the solution, right? And that eats up all your equivalent. Even if you add excess here, this will just soak that up, and the alkoxide will grab onto the magnesium and stop the reaction at that point. So when you work this reaction up here with water, you just get this back, the same starting material. Okay. Well, that's a frustration. You get 0% yield of the desired product if you have an alcohol or any functional group that has a proton that's acidic enough, right? And this is certainly acidic enough there for that. The pKa of an alkane is 55. So that means the Grignard reagent is super basic. Anything that can donate a proton like that will do it. But we want the addition here. So what we do first is react it with the tert-butyl dimethyl silyl-chloride, okay? And we abbreviate that as TBDMS chloride. Well, I guess that's a long acronym. Sometimes we just say TBS chloride, okay? In fact, that's what most chemists use, just TBS chloride. The book uses TBDMS, TBDMS chloride. This is a reagent, tert-butyl on a silyl. Silyl's in the same group as carbon, so 4 valence electrons, so valency of 4. 1 bond to the tert-butyl, here's 2 methyls, and then 1 bond to the chloride. Chloride's a leaving group, and this occurs in such a way that we get this. We get the tert-butyl dimethyl silyl group on the alcohol, okay? And usually some base is added in there, some pyridine as base, which when the alcohol adds here, and then the leaving group departs, you have to deprotonate this alcohol with pyridine. and that can be filtered off or purified away. The silyl group then stays on covalently with the alcohol. We call this silyl ether. Okay, so it's like a carbon-oxygen bond. It's a little more labile. It can be taken off. Okay, but it's on there temporarily. So this is called a protecting group. Why do we call it a protecting group? Well, now there's no proton on this alcohol, right? It's got this big silicon group there, which does not then transfer a proton to a Grignard reagent or other reactive reagents and keeps that functional group protected. Now we can do our Grignard. So on this, we can add whatever reagent we want there, methyl magnesium bromide, quench with water, and we can get our tertiary alcohol. And the protecting group, you see, TBS, and I'll use the shorter one, TBS. I think your book uses TBDMS. That's too much. TBS protecting group on this alcohol. It's not an alcohol right now. It's a silyl ether protecting group, you see, that enabled the Grignard reagent. There's no proton labile thing that can come off there. But this is still not the product we desired overall. So there's another step you got to know, and that's with tetrabutyl ammonium fluoride, TBAF. Yet another acronym, sorry. So yeah, TBS and now TBAF. And what's TBAF going to do? Well, it's going to take off that silicon protecting group. And yeah, here's a little bit on the mechanism. Fluoride has a high affinity for silicon that will attack the silyl group, eventually transferring a proton off of there. This is in water, or alcohol is added in the second step, and that protonates this position. So the TBAF takes that off. Where else does silicon end up? It ends up like this, okay, as the silyl fluoride. And that's often easily purified or washed away. You don't need to worry about it. But here we get our ketone that underwent the Grignard finally, and our protected primary alcohol that went along for the ride there. So yeah, protecting groups, simple protecting group like this is all I expect you to know. Yeah, there might be a couple homework problems that use this kind of strategy. Let's go back now to some synthesis problems. Let's do a couple harder problems maybe and see how we're doing on that. And again, this combines with some reactions from 351. Now on a quiz or a test, we're not just going to give you a bunch of reactions from 351, but they can be enabling reactions to help us with an oxidation or a reduction or a transformation like you've seen before of alcohol to a halide, whatever. Let's see a multi-step synthesis here. And we'll go in the forward direction first here. Let's start with bromobenzene, and we'll react with magnesium first, and then we'll react with this epoxide. Then we'll react with phosphorus tribromide. Then we'll react with magnesium again and add in CO2. What is the product? So this is kind of like the multi-step electrophilic aromatic substitutions, right? Here we've got a 3-step thing. Let's see. What's our first step here? The magnesium and the aromatic bromide. Yeah, that's forming the phenyl magnesium bromide. Okay. And then we dump in the epoxide here. And the epoxide's electrophilic. Remember, due to ring strain, you can break that carbon-oxygen bond, unlike the solvent, right? It's in THF. But that's a 5-member ring, not strained. But the 3-member ring is strained here. Where are we going to add? We're going to add on the end there, right? So let's keep track of this. We've got phenyl adding to that position. And then we've got that after quenching with water, all right? Let's make sure we got it right. 1, 2, 3 carbons. 1, 2, 3. It's kind of easy to lose track of your carbons with epoxides. And the phenyl, yeah, the benzene's attached right there, and then quenched with water. Yeah, that should be the product. Okay, what do we do with phosphorus tribromide with an alcohol? Yeah, we convert it to the bromide. Okay, that's your 351 reaction. More magnesium. What do we do there? Well, we generate the Grignard reaction, very versatile. We can have sp3, sp2 hybridized halides. We can make all sorts of primary, secondary, tertiary halides. All will form these great Grignard reagents. And then CO2, what's up with that? And then at the end, we neutralize with enough acid to get the neutral product. So remember the reaction with CO2 and the Grignard? CO2, draw it out. It's two carbonyls. The carbon's electrophilic, right? Push the electrons out, push them in toward the carbon. That's just like any other carbonyl addition. It's not really any different, but it'll give a different product, right? Once we quench with that, what's our product? Yeah, it'll be the carboxylic acid. Okay. Now that's a pretty complicated product, right? We started with a very simple bromobenzene. In fact, we could have started with benzene, right? We could have done the electrophilic aromatic bromination with Br2 and ferric bromide, right? Could have added another step here, but what? One here, and we don't isolate the Grignard reagent. We dump in the electrophile here in a subsequent step and then quench with water, you see. Here was our bond, strategic bond, elongating the Grignard by 2 carbons, but this was also on the epoxide, right? And why did we add here? There's 2 spots we could have added to, right? We added here, right? That's the primary position. The secondary position. This is a bimolecular reaction. The collision between these two things dictate the reactivity. So this is a strong nucleophile, charged nucleophile, you could say. It's going to want to go to the primary position. Okay. And then a lot of things we could have done here. We could have oxidized to a ketone and done some other stuff. What did we do? We brominated and then did the new Grignard and then the carbon dioxide. Tougher problem, and I'm showing it in the forward direction, okay? Let's look at a couple here in the reverse direction. So this is more of a synthetic planning thing again here. How about this? And let's make this from alcohols, 4 carbons and less, okay? Now we've got a ketone here with 2 different groups on the side. So where's our strategic bond? Well, how about right there, right? Well, first of all, how about that bond? Let's think about that because we can go back to the alcohol and then what? Oxidize with PCC, okay? Now, why did I pick that bond? Well, that becomes a strategic bond for what? The Grignard reaction, right? So then we could go back to the, and I'm showing the forward arrows. We're planning backwards, so I'm not drawing those open arrows. So that's a little bit different maybe for you. So we can go to that aldehyde and what? This Grignard. The magnesium, and then we got a tert-butyl there, okay? So how do we make these 4 carbons to the left? Well, that's easy. That came from this alcohol. That's fine. Oh, that's just more PCC. You see why PCC is so useful, right? In oxidized secondary alcohols to ketones and primary alcohols to aldehydes, okay? This one, we could have used the chromium. Yeah, there are alternative things here. What about this? This came from the bromide, which looked like that. But that's what, 6 carbons. We've got to deal with that. How do we make this? Well, let's think about this coming from an alcohol, right? The tert-butyl group on there. And this would be what? Phosphorus tribromide. Yep. And how do we make this? There's a couple things we could do there. I like this approach. Well, we could think this is a primary alcohol, right? We could have this Grignard, bromide, and then what aldehyde would it be? Yeah, formaldehyde. Now that would do it. But you see, this is 5 carbons, right? The tert-butyl and then a methylene right here. Adding the aldehyde give the primary alcohol. That'd be fine. Or what could we do here? We could have this Grignard, and yeah, the epoxide, okay? And that would go directly to this after quenching with water, right? And there you've got, what, 2 carbons, and then you've got the 4 carbons there. So we'd have to show how to make this. We'd make that from the tert-butyl bromide, phosphorus tribromide. Oh, no, well, this one would be fine with HBr. That'd be the cheaper way to go. Oh, I'm sorry, what am I doing here? This step here would just be the magnesium. Okay. This step here would come from the alcohol, right? Okay, yeah, that would be HBr. Okay. And some people worry about ethylene. Where do we get ethylene from? Ethylene comes from the alkene. Alkene to ethylene oxide here. Yep, MCPBA. Remember that? Metachloroperbenzoic acid. That goes back to chapter 9, I think, in 351. And if we're making this from alcohols, how do we get this? Well, that would have to come from ethanol, and we'd have to dehydrate it, right? With strong acid and heat. Get the alkene and then epoxidize. So, yeah, a couple different steps. That's using this as a strategic bond here. We could come up with this approach using that as a strategic bond. Then we'd have the aldehyde over here and a propyl Grignard adding here as a nucleophile. And I think you can go through that and do some planning there on that also. Anyway, okay. Yep, there's a couple there. Let's see this one. How about one with an alkene in it? And, well, no, how about one with a little more branching to it, maybe? And this one, yeah, this one has some unique structures to it in that we're branched right at the alpha position and branched at this beta position. So, yeah, these are your alpha positions, your beta position. And what you can recognize here is if you think of that bond as being strategic, you can do a different type of reaction, right? This would come back to what? This would come back to alpha beta unsaturated at that beta position. You also have this methyl here that would be important. And so what could we add here? Well, yeah, we could add the dibutyl cuprate, okay? And that would work to form that product. And then you'd quench with water, add the dibutyl. Remember, you're adding here conjugate addition at the beta position, and then you have the enolate. Then the enolate gets protonated with the water at that position. So yeah, that would be using a cuprate reaction as a strategic step. And then getting to here, what could we do? Well, it's a couple things we could do here. We could think of this bond as being strategic, and it would go back to an alcohol here, maybe, that's branched. And we'd have to oxidize to a aldehyde. And then what would we have to add to the aldehyde? Well, we'd have to add this vinyl Grignard, okay? Okay, so we'd have that vinyl bromide. And that's okay. You know, we have a lot of ways we can make vinyl bromides. That would come from this. Okay. How would we make that? Well, this would come from dibromo propane. And what would this be? One equivalent of potassium TP-toxide do one E2 reaction there to form the more substitute alkene there. That one would come off before this one over here. And then this would be what? Magnesium. And then add to the aldehyde. This would come from that, PCC. Yep. And, oh, we'd have to do another PCC reaction here, right? So after this adds, right, we'd get an alcohol here, sorry. Yeah. We get this allyl alcohol. This would have to be oxidized with more PCC. Yep, to there. So the vinyl addition here to this aldehyde would give us this unsaturated alcohol. And then how do we get this? let's see, there's a couple things we can do there. Here it's a primary alcohol, so if we add this Grignard magnesium, that would form the Grignard. And then what do we add to that? We add the formaldehyde. Yeah, and then we'd quench with water, and that would give us the primary alcohol. Yeah. So, yeah. That one looks a little bit harder. You know, we could have thought about this just using those as strategic bonds and thinking about that. There'd be some other things we could have tried there, opening those up. But yeah, this is one way to make that more complicated structure. Very good. So yeah, maybe we'll end a little early for this first hour, but be ready for the second hour here. And let's take a 10-minute break. Stay tuned for what? Chapter 21 coming up here, the second hour of class. Very good.